Good afternoon. Welcome to the penultimate physics lecture. There's one more after this. It is Physics 4B Video Lecture 26. And I had a couple requests for homework problems, so let's look at that and then we'll wrap up some really interesting material that we had set up last time with the time-dependent circuit. Okay, so the problems were chapter 28, problems 38 and 43. I'm going to do the more difficult of the two. Chapter 28, 43, problem 43. Problem 38 is pretty much the content of our next quiz. And okay, these are some of my favorite problems right here. So let's look at this 2843. Homework review 2843. So the scenario is that we have this ramp, opening angle theta, and I'll try to do some perspective here. And there's the bar sliding down it. This time there's a mass m of the bar and it has a length L. That perspective's not so good. Let's try this again. There we go. Okay. So yeah, this bar is sliding down the frictionless track and we've got the B field vertically here. We've got a resistor built in at the end. And this is that same circuit we talked about before, except that now it's on a slope. So instead of us pushing this, it just slides down without friction. Of course, there's that force pushing back on it. And that's what the problem's going to have us do. So let's see, how's our perspective here? Good enough. Okay. So yeah, there's that circuit, I'll put in red, of the current going through here. So what we could do is Faraday's law. When I derived this the first time, there were several more considerations to actually get the motional EMF. But Faraday's law makes this a lot easier. So the EMF is, and we don't have to worry about the sign right now. We're just going for the magnitudes. But okay, I'll put the sign in, but we're not going to worry about it. The magnetic flux time derivative, in fact, here'd be, right, problems like this, we work the direction out by hand, so to speak. So there's the EMF, d phi dt, that's Faraday's law, and we have B cosine of theta, because that's the flux at that angle. You can just take angle goes to 90 degrees and you would have zero flux. So you know that's the right one there. And then you have area. So the area for the flux is going to be L delta X. But since it's per time, it's L times V. Okay? And V is the speed that we're going down that angle. So there's the EMF. Let's even number these things. The second thing we're going to have is a current. And the current is just going to be E over R. That is what? Ohm's law. Right? That's a voltage. And the third thing we're going to have is a force. And we have that force is equal to I L cross B, and under these circumstances, magnitude-wise, we're going to have I L, and then the cross product is going to give us B cos theta. Let's send that up there. So now we have all the ingredients. Keep numbering. So F, and by the way, why the cosine of theta? That actually comes out of a cross product, but you would need the surface normal, or you need the cross product of this current with that vector up there. Okay. The way we see it's the cosine theta again is if we take the limiting case. Okay. If theta were to be 90 degrees, then the velocity v and the field B would be anti-parallel, therefore it would vanish. Therefore the cross product would vanish. Okay, so good. So we've got that, and we have, I'm just going to plug in. For I, we plug in this E over R. And then we've got the LB cos theta. But of course, this E here is LB cos theta V. So we end up with LB cos theta squared V divided by R. F. Okay. So I'm pretty sure that's what the answer is. No vector here. Is that right? Yeah, LB cos theta all squared V over R. Now then there's a question about the terminal speed, and that's interesting because as this thing picks up speed, the force becomes ever greater with the speed. So the force increases, and it's going to have to balance out the gravitational force, which is going to have a component that's parallel to the slope. So 4, 5. So for the final part here, we have F. I'm going to write F terminal, and I'll just LB cos theta squared. I see I went to a lowercase l, that's all right. LB cos theta squared over R V terminal. Yeah, what's that going to be? That's going to be mg sine of theta. Okay. And again, we know that if theta goes to pi over 2, it just turns into mg straight down, free fall. If theta goes to 0, of course, we're horizontal. We have no gravitational driving force. So go ahead and take this and solve for V terminal, and you're good. Okay, yeah, I like this problem. I like this whole scenario because it's linking the mechanical and the electrical concepts perfectly. This is a machine for producing, for obtaining power. If we were to keep going, we'd say, well, I squared R is the power being dissipated by that resistor. Okay, good. Let's see. What's next on our agenda? Okay, yeah, next we have that circuit. I had set up the equations, and I'm going to continue with that. That was a circuit with a resistor, a battery, and an inductor. An inductance whose symbol is a coil. So there's some really important physics here. And our goal with everything we're doing in this hour is to, at the end, somehow tie it into the electromagnetic wave phenomenon, production of those that we had talked about. Okay, good. Let's see. We have the this is the RL circuit. Okay. RL circuit. So let's just draw it. We had a battery as our power source, and then we had a resistor, and we had, did I draw it in this picture? I've got it right here. L. Okay. and we applied Kirchhoff's law once around. E minus IR minus L di dt is equal to 0. So we're going to do two things with this equation. We'll leave it up here. First thing we want to do is integrate it to find I of t. So integrate to obtain current as a function of time. And we have L di dt. We're going to separate variables. L di dt e minus IR. And we can even pull an R out. R times E over R minus I. That'll be a little better. And when we separate the variables, we're going to have dt times R over L. You know, we just treat this algebraically. So I'm solving, I've got dt times R over L on one side, and I have di divided by E minus IR on the other. That's called separation of variables, and then we integrate both sides. So one thing we can do, you'll notice I'm missing something there. So dt over R. Consult here. Oh, yeah, I forgot that last step, so I pulled the R. Yeah, I did on that one. Yeah, well, I was just looking at these two. We're looking at these here. Okay, so dt R over L. I've got the E over R minus I. Okay, I'm going to rewrite this. There's actually a lesson here. dt, let's go ahead and put the L over R in the denominator. di E over R minus I. So the way I just caught that mistake was that I was looking at dimensionless expressions on one side, and then I have to have a dimensionless expression on the other side. So this really is dimensionless. L over R is actually a time, and of course I in the numerator and E over R and I in the denominator have the same units. Okay, so good. So let's go ahead and integrate this. We have 1 divided by this L over R, that's going to be our time constant. I integrated to t, and here when I integrate, I'll put my sign here, I'm going to have minus the natural log of E over R minus I from I sub 0 to I. Okay. And that will be minus the natural log of E over R minus I divided by E over R minus I sub 0. So all we have to do now is exponentiate both sides and then solve for I and see what comes out. And we have, take the minus sign over to here, e to the minus t over this L over R is equal to I divided by E over R minus I0, and we need a little more room here. E over R minus I is equal to, not so fast, minus I0 times E to the minus T over R over L. L over R. So finally solving for I. We have E over R times okay. Letting I0 equal 0. That goes back to our goal here. We're going to start with, let's go ahead and repair this. What we're doing is we're starting with an open switch and we close the switch at time equals 0. So at time equals 0, so close switch at t equals 0. I'll kind of draw it like that. So at t equals 0, we have I sub 0 equals 0. So this was more general than we needed. And that simplifies things nicely. So I of t is equal to E over R 1 minus e to the minus t divided by tau. So I've given this ratio here the name of a time constant, and what we want to do next is just write this up here, graph it, and understand it. Good. So yeah, let's make a big graph. It's a basic but important operation here, and yeah, we still have this stuff to look at, which is good. So what we have is, let's rewrite this, I of t, E over R 1 minus e to the minus t over tau. This time constant is equal to L divided by R. And if you graph this, you'll see that when t is equal to 0, we have 1 minus e to the 0. 1 minus 1 is 0. So we're starting with 0 current. That's when we close the switch. And then when t goes to infinity, e to the minus t goes to 0, and we're just left with the constant current E over R. So we'll put that right here as a dotted line, and we see that we just approach that asymptotically. Okay. There's our graph, and this is the time constant. So I think we had something like this before with our capacitors. When the time is equal to the time constant, we have 1 minus 1 divided by E. So it's about 1 minus 1/3, so that's roughly 2/3, very roughly. But that sets the scale, because within a couple time constants, it's pretty much completely saturated. Which is to say, within a couple of time constants, you are at a constant current. But it builds up like we're showing here. Good. Okay. So we've got the picture of the circuit up. We can revisit this thing. So we closed the switch, current started flowing. Now we know that power is being burned, so to speak, in the resistor the whole time. But that's where, that's where the heat is being generated. So we have to see what's going on with the inductor here. And for that, we go back to this differential equation and multiply it by I. Yeah, multiply it by I. So next, multiply the differential equation. You could name it star, whatever, by I, and we'll turn it into this equation here. P is equal to EI is equal to I squared R plus, right? I brought the IR minus L di dt over to the right side, multiplying it by R, so L I di dt. So this was my equation. Just brought that over to the right side, multiplied by I. And what I'm recognizing is that is a power. So that's why I'm calling it power there. So I actually have the power being used by the circuit, or P is equal to I squared R plus L I di dt. So this is the power being used by the circuit. Okay, so this is really interesting because this we know about already. That's what a resistor does. It gets hot, Joule heating. But this one we don't know about. Apparently, when you flick the switch, both of these terms, this is Joule heating and this is something else, have a contribution, because here's the answer, right? We know what's going on here. As time goes on, you're going to end up with a constant current, and therefore this resistor is going to be burning constant energy, producing constant heat. And this term is going to vanish. Okay. This term is going to vanish eventually because di dt is going to go to 0, because this is going to turn into a constant. So for the time that this was non-zero, apparently the inductor is storing energy. That's an energy, power times time. If you integrate this with respect to time, you're storing energy here. Here you're just burning energy. Here you're actually storing it in the inductor or in the magnetic field. So what we could do is we could actually integrate, if we were to integrate L I di dt from 0 to infinity, that would be, I'm going to call it U sub B, would be energy stored in the magnetic field. In the B field, now since we have the symbol of an inductor, we'd say the energy stored in this device, okay? In the inductor. So that's interesting. How much energy is that? We don't even have to do a fancy integration. What we could do is actually take the derivative of this, times I plug it in there, and so forth. But instead, we can just see that these, here, I'll go ahead and do this here. The short version, I can go ahead and get rid of this now. The short version of this is to just say we've got L integral I di from 0 to I, put a little prime here, integration variable, and that's L I squared over 2. And we'll actually be good to go. That'll do the trick, yeah. I squared over 2, okay? Because we've integrated from 0 to I. There's the 1/2. So we have energy stored in the inductor or stored in the magnetic field. I'll call it L is equal to 1/2 L I squared. Now, if you actually put in the expression for the inductance of a coil, which is what our picture is there, you get energy density. I'll just write this down. Do I have a... Okay, I'm using B, so, well, yeah. Let's go ahead and put a B here, because the lowercase use of B is going to be 1 over 2 mu naught B squared. And we'll stick with that, B squared. When you integrate this up with volume, then you'll end up with this. Energy density in the B field. Good. We're actually going to continue using this though for our next project. Actually, let me even add here, recall energy density stored in the E field was 1/2 epsilon naught E squared. But again, that's just as a reminder. I want to continue on with this, and in fact the capacitor. So I'm going to introduce one more important circuit. Okay, great. So we got plenty of time. Okay, so before we move on, what we've seen is the time dependence of a circuit, because any circuit really has built-in inductance, okay? And the current doesn't just leap up from 0 to the full value, but rather it grows gradually, saturates, and there's a time constant in which that's involved. So that was the analysis of this circuit. What we're next going to do is talk about the circuit that has a capacitor and an inductor. See what I can erase here. I'll send this up. And of course, what we learned here from this analysis was that we have that energy stored in the magnetic field. So make a note of that. Energy is stored in the magnetic field. That's the significance of this expression and of this concrete one. Okay, our next circuit, I'm going to skip this one here. Good. So next, the LC circuit. So let's just draw what we're looking at now. The idea is here we have a charged capacitor and it's connected with inductor, and we're going to have a switch that we're going to throw, close the switch at t equals 0. So initially this thing is charged, okay? You know, we can have plus Q and minus Q. So initially we have a charged capacitor. And there's nothing going on with this inductor here. But we remember from earlier work that there was energy stored in a charged capacitor. So initially, energy U is equal to U sub C is equal to Q squared over 2C. So that's the initial energy in the capacitor. And I have here maximum, and we'll see why. So next, close the switch. And there's no resistor in here, and that's where the energy would be lost in a resistor, right? Energy would be burned in a resistor, produce heat. So since there's no resistor in here, after we close the switch, the energy is going to remain constant. Close the switch, then U is equal to U sub C plus U sub B, or I could have called it U sub L. We got to make up my mind on that one, right? How about U sub L? Well, U sub B, since it's up there on the board. It's constant, and the reason it's constant is, of course, no resistor. Okay. So what do we have? We have U is equal to Q squared over 2C plus 1/2 L I squared. Physically, what's happening, we close the switch, a current starts to flow, okay? So the current starts to flow, and we know the current flows through here, B field's going to be built up, B squared. There's going to be energy distributed, so the energy is going to decrease here and increase here. So our next step is to take the time derivative of this expression here. We'll take the time derivative, but we know that the energy is constant, so the time derivative equals 0. So here's our next task. I can go ahead and erase this now. So du dt must be equal to 0. But what is that time derivative? We have, implicitly, we have 0 equals 1/2, so 1 over 2c, 2q dq dt, and we have 1/2 times L, 2I di dt. And we're going to be able to turn this into a differential equation of second order. So first of all, this is equal to 0. This is equal to 0. I got the 0 over here. Now the dq dt is by definition equal to I. So I can strike these both. Also the 2's cancel. And I have di dt, L di dt is equal to minus Q over C, put the minus sign over, minus Q over C. And there's a little more room here. So we have di dt is equal to minus 1 over LC times Q. But we already said that I is equal to dq dt, so that will be a second derivative. So d dt of dq dt, that's the left side, minus q over LC, and finally d squared q dt squared is equal to minus 1 over LC times Q. So at this point we have to recognize this as the harmonic oscillator differential equation. And I'll put that up because we've studied it before in terms of masses and springs, and we actually had the very same form. Yeah. So I gotta make some room here. But actually, let's keep this picture up here. So we have d squared q dt squared minus 1 over LC times Q. And we're going to compare this to what we had with oscillations. Of a mass on a spring. So when we had oscillations of the mass on a spring, we had d squared x dt squared equals minus, well, I'll do it in 2 steps just to remind you, minus kx. This was Hooke's law for a mass on a spring. So d squared x dt squared was equal to minus k over mx, and the solution x of t, and you can of course test this just by taking derivatives, was some constant called the amplitude cosine omega t plus some phase alpha, and omega was equal to the root k over m. Okay. So this is what we've studied before, and what we're doing is we're going to take these results and just relabel this. Okay. So what we can say is q of t is equal to, instead of amplitude, we'll just say q max. I need a little more room. So q of t equals q max, that's fine, cosine omega t plus alpha. Yeah, what is our omega now? Root whatever this factor was. That's the omega. The square root of the constant factor in front of the variable. So omega is equal to square root of 1 divided by LC. And that's the frequency of oscillation. Anything else to say there? Yeah, well, we can take derivatives, but I don't see any point right now. What we have, though, is oscillations. We have harmonic oscillations of the charge. Very important. So we have an oscillating charge. If we take the derivative of this, we'll get an oscillating current. And maybe that's not wrong to talk about either, because we get current going through here, but it's oscillating, so it's going back and forth. So this thing is storing energy and setting up a current back to here. This stored the energy first. What we basically have is the energy going back and forth between the capacitor and the inductor. So we're getting oscillations. So let's write this oscillating charge, and then note also oscillating current, because dq dt is just going to be the minus the sign of this, the little omega pulled out, and that current will also be oscillating. So note also current. So oscillating is the point right here. Remember we talked about electromagnetic waves being generated by accelerated charges. Well, if you have oscillating charge distribution back and forth here, you have the accelerating charges right here. Okay. Here you don't have, well, you have the currents, but here you explicitly have the accelerating charge, and the field's changing sign, and that's where you're actually going to be able to produce electromagnetic waves. So accelerating charges over here, you can produce waves. If waves come into this circuit element, they can set up an oscillation here as well. Okay. So when Hertz actually was able to send and receive electromagnetic waves, it was with an oscillating circuit, roughly of this type. Fundamentally of this type. Okay, I'm going to consult the clock. Okay, of course, many more things in our chapter, but we're going to leave it here with these oscillating circuits. The next step would be the Rlc circuit, which takes some time to set up. And the next step after that would be the driven Rlc circuit. Let me go ahead and just write those down. In fact, I'll go ahead and just give a rough outline of what happens here, okay? So we now have this oscillating circuit. So here's the progression. LC circuit. That's an oscillator. Yeah, if you wanted to graph it, your Q of T, you've got an oscillator. Okay. If you want to graph the current, you're also going to have an oscillation. So the next circuit would be the Rlc circuit. Now we know that the resistor dissipates energy. Let's go ahead and just draw it like this. So we would have, we would start with our Q max over here, and we would not just have, C and L, so there's C, we would also have R L. So the difference here, provided the R is not too great, we're also going to get oscillations, but we're going to get damped oscillations because the original energy stored here will eventually be all dissipated in the resistor. So what you get is damped oscillations. And the graph for those, since we're graphing these things, so 3 Rlc circuit, the graph in terms of time here, and yeah, we could still use Q. It would, but what we do is we draw a little, let's write it out here, so that Q T is going to be, I'll just write proportional E to the minus, I would have to write it down. There's going to be an E to the minus T. I'm just going to write exponential decay. So there's an envelope in your graph. It's going to do this. And the next circuit would be, so 4 would be the driven Rlc circuit. Right, and this has a complete analogy with the mechanical treatment that you do when you talk about resonance. Yeah. So there's a complete mechanical analog to these things. That's how it goes. And with the driven Rlc circuit, you actually get into a lot more technical details that we don't have time for. But this is basically what it is. We're going to leave it at that. Again, it was these devices that allowed the production and reception of electromagnetic waves. So that's why we wanted to make sure we get right here. Good, see you next time. That'll be the review.